Hey everyone, welcome back. We're going to go ahead and finish off our discussion of the doubly linked list by looking at the remove algorithm. And this algorithm will be for removing a node from the doubly linked list. This will be very similar to the remove algorithm for a singly linked list with the additional overhead of having to deal with that prev pointer. So we'll look at the algorithm, we'll see how it works by tracing through it, and we'll finish up with some analysis of the performance of the algorithm. So for our algorithm to do its job, it's going to need to have three things in scope: the head and the tail references in scope, as well as a key value in scope. And it's going to be this value that we search our list for. And if we find it, then we're going to remove the node that's storing it. So that key value will be in the node that we want to remove. If we don't find it, then we won't do anything. But if we do find it, we're going to remove the node and make sure that all of our references are maintained. All of our links remain unbroken. So we're going to have to look at a few different scenarios. The first scenario we'll look at is what happens with our algorithm if we are dealing with an empty list. And if we have an empty list, then we're going to have a picture that looks like this, where both the tail and the head reference are referring to null. So how does the algorithm work? We create those temporary references. We initialize P with the head reference, and then we initialize Q with null. So we then move on to a while loop, and the while loop is going to be what we use to traverse the list, searching for the node we want to remove. So while P not null, well, right away, that's false. Loop's done because P is referring to null. So then we move on to the next if statement, and we check to see if P is null. If it is, there's nothing to do, so we return. And in this scenario, that's the case. So we're done, we're out of our algorithm, and nothing changes. There was nothing to remove because it was an empty list, so everything works as it should for an empty list. Now let's look at scenario 2. And in this scenario, we're going to have a list that contains one node. And we're going to make sure that it handles it, whether the value is found or not. So let us assume that the value is not found, that K is not in the list. So the algorithm begins with the temporary references, P and Q. P is initialized to the head reference and Q is initialized to null. So we go to our while loop, while P not null, that's true. And the value in that node that P is referring to is not containing the value we're searching for, that key value K. So that is true as well. So since they're both true, we're going to advance our references. So we overwrite the contents of Q with the contents of P. So Q now has the memory address of our node. And then we overwrite the contents of P with the contents of the reference in the node that P is referring to. In this case, that's null. Go to the top of the loop. While P not null, false. So our loop is done. Short circuit evaluation ensures that the second expression does not get evaluated. So no null reference exceptions will be thrown. So we go on to our if statement. If P is null, that's true. Return, we're done. Makes sense. We didn't find the value that we were searching for, so there's nothing to remove. So now let's examine if we do find the node in the list. So algorithm starts. We've got our temporary reference P initialized to the head reference. We've got our temporary reference Q, which is initialized to null. And we move to our while loop. While P not null, that's true. And the value in the node P is referring to, well, that does not equal the value we're looking for. Well, in that case, it's false. So the loop is done. P is referring to the node that contains the value that we want. So we move on to our if. If P null, return. That's false because P's got the memory address of the node that it's referring to. And so then we go down and look at a couple of different if else's. So if Q is null, that is true because Q was never updated and it was initialized with null. So then we're going to update the head reference by assigning to it the reference that's in the node that P is referring to. So we're just overwriting what's in the head reference with null in this case. So we skip the else and then we go down to the next if. If P next is null, that's true because the contents of the reference in the node that P is referring to is null. So since that's true, we update our tail reference to Q. Now what's in Q? Null. So both our tail and our head are referring to null, which is what we're going to want because we're going to be removing the only node in the list. So that's going to leave us with an empty list. So we skip that else. We go to the very last statement, which is to overwrite the contents of P with null, thereby eliminating the last reference referring to the node we want to remove. So once that happens, the garbage collector comes along and removes it from memory. So what are we left with? Head referring to null, tail referring to null, and an empty list. The two temporary local references leave scope, so they're gone too. So we're just left with head and tail referring to null. So we have a successful execution of our algorithm in that scenario as well. So next up, let's look at a scenario where we've got multiple nodes in our list, and we want to make sure that we can remove the first node in the list without any problems. So we've got our tail reference and our head reference set, and we've got two nodes. So we're going to get rid of this very first node here. That's what we're going to search for. So we look at our algorithm. Local reference P is initialized with the head reference. Local reference, temporary reference Q is initialized to null. And then we go to our while loop. While P not null, that's true. P is referring to the head node. And P dot I not equal to K, that's false because K is in, that value K is in that first node. So the loop's done. So we go down to the if, the first if there, if P equals null, that's false because P is referring to the head node. So then we move on to the if statement, the next if statement. If Q is null, true, because we can see that Q is referring to null right here. So we set H to P next, as we did in the previous example. So our head reference is now pointing to the node that follows the head node or the former head node. And then we go to the next if else. If P next equals null, that's false because the reference, the next reference in the node referred to by P, in fact, contains the memory address of that following node. So we kick down to the else and we do P next prev set to Q. So what's P next prev? So this is P, this is our next, this is our prev. So we're going to change that prev to Q, which is null. And then once we've done that, we move down to the very last statement and we set P to null. So P is now referring to nothing. And that causes the last reference to the head node that contained K to no longer refer to that node. So the garbage collector comes along, removes the K node from memory. Now let's check our references. The head reference refers to a node, and then that node refers to null. So we traverse in that forwards direction perfectly fine. And then we look at our tail reference. That refers to the last node, the tail node, which is also the head node in this case. And then its prev goes to null. So we're also good going back to front. So our links are maintained front to back and back to front. So next scenario, we're going to have a multi-node list, and we want to get rid of a node that's at the end of the list. And make sure that all of our links stay maintained. The node gets removed and everything is fine. And we can continue our traversals in both directions, front to back and back to front. So this scenario, the value K that we're searching for is in the last node. Remove algorithm begins. We create a temporary local reference P, initialize it to the head reference. So it's referring to the head node. And then we're going to create a temporary reference Q and we're going to initialize it to null. Then we kick down to our while loop. While P not null, true, because P is referring to the head node. And while the value in that node that P is referring to is not what we're searching for, also true, because the K value is in the last node, we're going to update our Q and our P. So Q gets updated to the contents of P. So it's not going to refer to the head node. And then P gets updated to P next. So it is now going to refer to the next node in our list. Go back up to the top of the loop. While P not null, that's still true. And the value in the node P is referring to is not the value we're searching for, K. That is also true. Update the contents of Q with the contents of P. So Q now refers to the same node P refers to. And then we update the contents of P with P next. So now our P reference is referring to the tail node. And we go to the top of our loop. While P not null, true. And P dot I not equal to K, false, because K is in fact in that node that P is referring to. So the loop's done. Now we move on to our first if P null, return false because P is referring to the last node. And then we check our next if statement. If Q is null, that's false because Q is referring to this node right here. So we kick down to the else there, Q next, set to P next. So what's Q next? It's the reference in the node referred to by Q, the next reference. So we're going to set that to P next. Now what's P next? It is the next reference in the node referred to by P. So we overwrite Q next with P next. Then we go to our next if statement. If P next is null, that's true because P next is referring to null. So what do we do then? we set T to Q. So we're going to overwrite the contents of our T reference with the contents of our Q reference. The Q reference refers to that node. So we are going to update T to refer to the same node Q is referring to. Once that's done, we go to our last statement, which is to update P to null, which means that it's no longer going to be referring to this last node. And since there's no other references referring to that last node, the garbage collector comes along, removes that node from memory. Algorithm's done. Our local references leave memory as well. And so we're left with a picture that looks like this. Now, is this going to be correct? Are our links maintained? We start at the head reference that points at the head node. Then we check the head node's next reference. That goes to the tail node. We check the tail node's next reference. That goes to null. So if front to back traversal is maintained, then we look at our tail reference, and that refers to the tail node. We look at the tail node's prev. That moves to the node that preceded it. And then we check that node's prev, and that refers to null. So our back to front traversal is maintained as well. So our algorithm is handling that scenario as well. Finally, let's look at a scenario where we are going to remove a node that is in the middle of a list. We want to make sure that our algorithm handles that scenario, removes the node, and doesn't break any of the links in our list. So it means we're going to be removing that node right there in the middle. So we got our tail reference pointing to the tail node. That node's prev is pointing to the K node. The K node's prev is pointing to the head node. And the head node's prev is pointing to null. So our algorithm begins, and we've got our P reference initialized to the head reference. We've got our Q reference referring to null, and the loop kicks in. While P not null, true. And while the node that P is referring to does not contain K, that's true. Advance our Q reference. We're going to update it to P, and then we set P to P next. So our P reference is going to advance to the next node, go to the top of the loop while P not null, true, and P.I not equal to K. Now that's false because the node that P is referring to does contain the K. So the loop's done. Move to the if. If P is null, return. That's false because P's got the memory address of the node that is storing K. So go to our next if statement. If Q null, false because Q's got the memory address of the head node. So we kick down to the else. Q next set to P next. So we're going to set Q next, which is this reference right here, to P next, which is this reference right here. So the next reference in the node referred to by Q is now referring to our tail node. So then we go to our final if else statement there. If P next is null, now that's false. Here's our P next, and it's referring to the tail node. So we're going to go down to the else, and we're going to set P next prev to Q. So this is P next, this is P next prev, and we're going to set it to Q. Now what's Q referring to? The head node. So we overwrite the memory address in the tail node's prev with the contents of Q. Once we've done that, we do our last statement, which is going to set the P reference to null. So once we do that, there's no references pointing at the node we want to remove anymore. So the garbage collector comes along and removes it from memory, thereby removing it from our list. Let's check our references. The local references, they leave scope, and so leave memory, and we're left with a picture that looks like that. So from our head reference, we can go to our head node. From our head node, we can go to our tail node, and from our tail node, we go to null. So front to back, we're fine. Now let's go the other direction. Tail reference to the tail node to the head node to null. So we can traverse our list from back to front. So our algorithm handles that scenario as well. So it looks like our algorithm is correct for removing a node from a doubly linked list. Now let's do a little bit of analysis here. So in each scenario, we had to create both of those references and initialize them to null. So that's two operations. Now, if we take a look at our while loop, we have to test this every single time for each node, and we have to test this every single time for each node. So that's two operations times n nodes. And then for each node, we have to do that statement and that statement as we're doing the traversal. So that's two additional operations per node. But when P is referring to null here at the end, then we're still having to do this operation one more time. But due to this short circuit evaluation, this doesn't happen, and the loop terminates So that doesn't happen that extra time. So we just have to add 1 in that scenario. So what we have is 4n plus 1. Now, worst case, certainly not if p is null, but we still have to test if p is null. So we're going to add that operation. And then we have our if else, right? So the first if else, we definitely have to do this test, check if q is null. So that's an additional operation. And then we're either going to do this one or this one. We're not doing both. So that's just one additional operation. And then we have to check if p next is null. That's an additional operation. But we're only going to do one of these other two, right? If it's true, we're setting t to q, or we're setting p next prev to q. So that's just one additional operation as well. And then finally, at the very end, we have to set our p to null. So that's one more operation as well. So let's combine all these terms. We got 4n plus 1, 2, 3, 4, 5, 6, 7, 8, 9, plus 9. So that is our big O. But we can reduce our big O through the magic of calculus and limits. So as n gets incredibly large, as it approaches infinity, infinity plus 9, we can get rid of that 9. 4 times infinity is still infinity. We can eliminate the 4. So we're left with an algorithm that is big O of n, or a linear time algorithm. So that's everything that I wanted to cover in this series of videos. As usual, if you're a student of mine, you have questions about any of the content presented in this series of videos, feel free to stop by my online Zoom office hours or email me through Canvas. Thanks for watching, and we'll see you next time.